Hello, in this video I'll be solving problem 6.13 of David J. Griffith's Intro to Electrodynamics 4th edition. Problem 6.13 reads, suppose the field inside a large piece of magnetic material is B naught, so that H naught is equal to 1 over mu naught multiplied by B naught minus M, where M is a frozen-in magnetization, meaning that it's constantly in the same position. A reads, now a small spherical cavity is hollowed out of the material, figure 6.21. I've included that right here so we can see what the sphere that we're hollowing out looks like. And now it wants us to find the field at the center of the cavity in terms of B naught and M, and also find H at the center of the cavity in terms of H naught and M. To solve this part, first we need to understand what we are removing and essentially hollowing out of the material, and that is a small sphere. Now, if you refer back to example 6.1 earlier in the book, we found that the magnetic field of a small sphere, or in general any sphere, is equal to 2/3 mu naught M. And what we're doing with this magnetic field of the sphere is removing it from our original magnetic material's magnetic field, which is just B naught. So we're finding that our new magnetic field B is equal to just the original B naught minus this field, which is 2/3 mu naught M. So the new field of our space, our magnetic material, is B naught minus 2/3 mu naught M. So next we want to find H at the center of the cavity in terms of H naught and M. Now in general, H is equal to 1 over mu naught times B minus M. However, at the center of the cavity, M should equal 0. So H at the center of the cavity would just simply be 1 over mu naught times B. Now, we want to find H with our new magnetic material, or our new magnetic field. So we'll plug in our value for B. So H is equal to 1 over mu naught times our new B, which is B naught minus 2/3 mu naught M, which when multiplied out, we get that H is equal to 1 over mu naught times B naught minus 2/3 M. However, we want to find H at the center of the cavity in terms of H naught and M. Now, if we look at the first part, we have a given H naught is equal to 1 over mu naught times B naught minus M. So if we write that out, we'll see that H naught is equal to 1 over mu naught times B naught minus M. Now, if we rearrange this by moving M to the left side and multiplying both sides by mu naught, we'll get our value for B naught that we can plug in for H. So we'll get that B naught is equal to mu naught times H naught plus M. So, plugging this into our value for H, we can solve for H at the center of the cavity in terms of H naught and M. So we'll get that our new H is equal to 1 over mu naught times our value for B naught, which is mu naught times H naught plus M minus 2/3 M, which when you multiply 1 over mu naught times our value for B naught, these just cancel out. So we'll end up with H is equal to H naught plus M minus 2/3 M, which with simple subtraction, we get that our value for H at the center of the cavity is equal to H naught plus 1/3 M. So that is the value for H at the center of our cavity with a hollowed out spherical small sphere. So part B wants us to do the same for a long needle-shaped cavity running parallel to M. Of course, here again is the needle that we're removing from our magnetic material. And we're going to follow the same process. We're going to see what the magnetic field of our removed shape is, and just subtract that from our original magnetic field B naught. So a long needle-shaped cavity is a long needle-shaped, like hollowing out process. And a long needle is essentially a long solenoid. And the magnetic field of a solenoid is simply equal to mu naught K, the surface current. However, we want the magnetic field in terms of course, B naught and M, as noted here in the original part. So we need to find out what our K value is. And K is generally equal to M cross the normal vector n hat. So we need to look at the coordinate plane and just the general directions of everything in our magnetic material to find out what K is. So drawing out our long solenoid, or the needle shaped, M is parallel to it, and we'll make this very simple and coordinate Z hat, the Z axis right through the center of our solenoid, so that M is in the same direction as Z hat. Ignore those little things. Now, how to find n hat, or our normal vector? We need to consider what we're actually doing. This is not an actual cylinder. This is not a solid cylinder. This is a hollowed out cavity within a giant magnetic material. So all around this hollowed out cavity is a solid space. So with that in mind, we'll understand that S hat should be pointing away from the cavity. So that makes inside of the cavity negative S hat, which, following our process, the normal vector to the surface would then be in the negative S hat direction. So our K, or the surface current, is traveling in the negative phi hat direction from crossing Z hat with negative S hat. And I'll show you this right now. K is equal to M Z hat direction cross multiplied with the negative S hat from our normal direction, our normal vector's direction, which when Z hat is crossed with negative S hat, we get M negative phi hat, which is equal to RK, our surface current direction. Now, by the rule of the right thumb, or by the right-hand rule, we would see that with K traveling in this direction, the magnetic field would be traveling in the negative Z hat direction, So the magnetic field would be in the negative Z hat direction, since it's equal to mu naught K, which can be replaced with M negative phi hat. However, we don't need to keep these all in mind when we're actually removing it from the magnetic material's original magnetic field, B naught. So when we're writing you do need to keep these in mind, but you can write it out blatantly. So the new field would be B is equal to B naught minus mu naught M. And you can include the negative phi hat. So that's our equation, our new magnetic field. With that, we now also want to find H at the center of the cavity in terms of H naught and M, which again, in general, H is equal to 1 over mu naught times B minus M. However, again, at the center of our cavity, M is equal to 0, so H is just equal to 1 over mu naught B at the center of our cavity. Now, plugging in our new value for B once again, we'll find our H is equal to 1 over mu naught times B naught minus mu naught M in the negative phi hat direction. Multiplying 1 over mu naught into our parentheses, we'll find that H is equal to 1 over mu naught B naught minus M in the negative phi hat direction. So again, we want to find H in terms of H naught and M though. So we'll plug in our same value that we found for B naught here, which is, let me see if I can underline it, or I'll just circle it. B naught should equal to this. So plugging that in down here, we see that H, not in red, H is equal to 1 over mu naught times our value for B naught, which is mu naught times H naught plus M, as seen right here. We'll get 1 over mu naught times mu naught H naught plus M. I believe it's plus M. Yes. Minus M in the negative phi hat direction. I don't think that's parentheses necessary. So multiplying 1 over mu naught into our parentheses, these cancel out. So H is equal to H naught plus M minus M. So H is simply equal to H naught. And this is the H at the center of our cavity. Now, for the final part, part C, we need to do the same for a thin wafer-shaped cavity perpendicular to M, which we can see here. Now, we can see that the wafer is very thin. However, it's the same shape as our needle, just very wide. So, we can consider this also as a solenoid, with a K traveling around it, the surface current. However, unlike our needle, this wafer can have very little loops around it. However, this needle can have extraneous amounts of loops. So that means that the magnetic field of this wafer that is produced is much less than the needle's magnetic field, since the eye will just be much weaker. So what this means is that when we actually remove our magnetic field of the wafer, we just get that B naught minus our mu naught M in negative phi hat direction. The subtracted magnetic field is just very small, and it's very, very small. So we can approximate that our new magnetic field is just essentially the original field. So we can say that the new magnetic field is simply B naught. To find H for this new space with this thin wafer-shaped cavity, we can find that our new value for plugging in our value for B. So as you see here, we would go through the steps. We'd go through the steps to get to the point where we need to plug in our new B value, and we'll just do that again once again. H is in general 1 over mu naught B minus M. However, at the center of this cavity, M will equal 0. So 1 over mu naught times B, our new B value, which is just B naught. So H is equal to 1 over mu naught times B naught, plugging in this value for our new magnetic material, magnetic field. So plugging in again the values for B naught in order to find H in terms of H naught and M, we find that H is equal to 1 over mu naught times our values again found right here for B naught, which is mu naught times H naught plus M. We find that H is equal to 1 over mu naught times, in parentheses, mu naught times, in parentheses, H naught plus M, which when you multiply 1 over mu naught into the parentheses, the mu naught cancels. So H for this new magnetic material with this thin wafer-shaped cavity is equal to H naught plus M. So with this, we have found the new magnetic field for each of these spaces, each of these cavities, and we have found the H at the center of each of the cavities as well. Thank you.